Students, this is Unit 1, the Alphabet and Grammar of Geometry, Lesson 1.4, Brain in Hand Problem Solving. You are right here in your video notes watching this on either the 1st or 2nd of September prior to class on the 3rd and the 4th. You want the location, the date and time, and don't forget to get a parent signature, teacher, mentor, guardian sign off. Please, no multitasking while you're doing this. This is a very, very important lesson. Let's start with some review here. I'd like you to take a shot at these two algebra problems on your own and then restart the video. Pause. Welcome back. Let's check your work here. We'll do this together. Taking a look. So we're going to cross multiply here, not cross cancel. That's very important. Let me show you what you should not have done. You cannot cancel across an equal sign. Notice what I just did there. I went across an equal sign and cancel stuff out. That is a no-no. You cannot cancel across an equal sign. You can't go across a neighbor's fence and steal from them. However, you can be really nice to your neighbor and you can multiply. So you can cross multiply. And notice when I do this, watch. Wait a minute, why didn't I multiply 6 times 9? That's because the key to multiplying is actually not multiplying. It's factoring. So I'm just going to leave it as 6 times 9. I'm going to divide by 2 here. And now I can factor this out. 2 goes in here 3 times. X equals 3 times 9, 27. And I am done. So the key to multiplying is actually not multiplying. It's factoring. Let's check your work here. You want to grab the -2 by circling and then draw the distributive arrows. Grab that -4 and distribute. Next line reads, we're going to have 8. -2 times +5, -10v. -2 times -6, double negative makes a positive. -4, that's -4v. Double negative makes a positive. That's 32. And then we have -3v. We collect like terms, and when we do that, I like to physically circle stuff as I collect it. So I'm circling all my V's. I'm underlining all my numbers. So I have here 8 plus 12, that's 20. And there's nothing to collect here, so it's -10v equals -4 minus 3, that's -7v plus 32. I get my variables on one side, my numbers on the other. So we have 20 equals, that's 3v plus 32. We're going to minus 32. And cancel. I'm going to bring this up here. That's going to be -12 equals 3v. Divide by 3. And we have our variable, v equals -4. Double check your work. So now we're getting into one of the most unusual lessons of the whole year. This is very distinctive in my class. It's called brain in hand problem solving. Here are some words you're going to become familiar with. Neuron, frontal cortex, digital immigrant, digital native, hypertext skimming, linear reading. So let me explain where this particular lesson comes from. I, as your teacher, am what's called a digital immigrant. That means I did not hit digital technology. Well, I won't tell you how long, but let's just say this. I wasn't a kid when I hit digital technology, nor was I a teen. So I am what they call a digital immigrant. So digital technology is something that I immigrated to. Obviously, I'm quite proficient at it, but I'm a digital immigrant. You, my students, you are what's called digital natives. You have grown up with digital technology from infancy. So what I started noticing in my classroom just a few years ago is I would be working with a student, let's say in tutoring, and I would draw a very simple problem on the board, something that looks like this. And I would just draw it on the board, and I would ask the student to solve it, and they would just look at it and look at it about 10 seconds, and then they would instantly say, I don't get it. After about 10 seconds, they're looking at a very simplistic problem. Notice very often where the hands were. Hands were tucked or not using, and a student would say, I don't get it, and I didn't understand why. And so I would take that student and I would force them hand over hand to draw, and they would sweep each angle, and then all of a sudden they'd say, oh, this is easy. After they physically put their hands on the diagram, then they saw it was a very easy problem, and we solved it within literally 45 seconds. What I was noticing is that I, as a digital immigrant, would instinctively physically interact with the diagram. I would trace, draw, sweep, write out my computations. And increasingly, my students in tutoring would simply look at stuff with their eyeballs and not process the information. Therefore, they got stuck. I don't get it, increasingly. So this entire lesson for the next half hour is to describe why a digital immigrant's brain is different from a digital native. And what does that mean for geometry class? And what are some things we need to get in the habit of doing? So before I go on, I'm going to discuss 4 key thoughts here. And some of this may be really new information to you. So don't freak out as I talk about it, and realize everything I say, notice I have researched references if you or your parents would like more information, or you can email me. So 4 key thoughts. Key thought number 1 is the fact that your fingertips are directly connected to your frontal cortex. Why is that important? Your frontal cortex, that's the front part of your brain, that's your conscious thinking part of your brain. Your reasoning skills, problem-solving skills, thinking about cause and effect, that's all in the frontal cortex. And guess what? Neurons from your fingers are directly connected and give input to your frontal cortex. That's the first key thought. Key thought number 2. This is very important for you to understand this. The use of digital technology is physically reshaping brain. Brain development is happening different from those of us who are digital immigrants to those of you who are digital natives. Let me explain why brains are developing and connecting differently. 1, you as a digital native, you keyboard more than you physically write, most of you. You click on stuff more than you physically colored, most likely. Your entertainment is predominantly digital technology and tablets. Therefore, the vast majority of you are interacting more in the digital world than you are in the physical world. And you're tapping screens more than you are physically touching physical models. Notice what's going on here is that this is all predominantly 2-dimensional, tapping, touching on screens versus living and interacting in the 3-dimensional world. And it's changing the way your brain thinks. Again, I have references right there. That's key thought number 2. Key thought number 1, your fingers are connected to your frontal cortex. Key thought number 2, technology, use of digital technology reshapes neurology of brains. Key thought number 3, and if you've never heard this, this may be shocking to you. And again, I have the references. Screen reading, reading from an iPad screen, a digital screen of any kind, is inherently different from reading from paper. whether it's note cards, binder paper, a physical book. It is your brain processes information inherently differently. The reason why is digital screens automatically put your eyeballs in default skimming mode. They kind of get into wander mode. That's because web pages are not designed for detailed reading. They're designed for 10-second skimming. And the looking at the screen itself causes the eyeballs to generally go into skim mode. That means when you're reading on a tablet, most of you are not reading in detail. Versus when we read on paper, we tend to go line by line, left to right, and it's a lot easier to pay attention to detail. So when you spend the majority of your time on screens, let's say you spend 80% of your time on screens and not even 20% of your time looking at actual magazines, newspapers, and books, your eyeballs can get stuck in skim mode. There's some techniques that'll help get you into detailed mode, but you just need to be conscious. Reading from a screen is different than reading on paper. Again, there are notations there. And the last and most important one for this class is that thought number 4, increased hand and finger usages increases brain function. The more you give physical input using your hands or your frontal cortex, the greater the neurons are going to be firing. Again, if this sounds like science fiction, you can check out my footnotes here. What does this mean in geometry? It means I'm going to be training you in something called brain in hand problem-solving techniques. And this is to help you overcome the global, when students look at problems, they just glance at a problem and immediately you just say, I don't get it. And because you don't get it, you kind of shut down. I quit. Why try? Many of you are asking, but Ms. Way, if I don't understand, how can I give effort and not quit? How can I do anything else but not quit if I don't understand? Guess what? I've got something for you that will be very helpful. You're going to learn how to process information through brain and hand techniques, which includes finger track with your finger on paper or screen, and make sure you're reading out loud. You're going to learn to draw, label, list, and cross out things. You're going to hear me in class constantly say, trace and sweep an angle, trace and mark the diagram, trace and stretch lines, trace and shade diagrams, finger block lengths. You're going to hear me use this term, squeeze a sponge. That means squeeze out all the information you can out of a problem, even when you don't understand something. You learn to ask yourself, well, what can I do? Rather than what should you do? I'm going to train you to write equations with 2 sides and an equal sign. You're going to learn to do what's called circle, plug, chug when you solve problems. You're going to physically block and label your answers. And you're going to learn to take a step back from your work and scratch your head and ask yourself, does this make sense? So to answer this question, if you don't understand, how can you give effort? Because if you don't understand, you don't give effort. That's what many of you are kind of stuck in. But the problem is, effort is what gives understanding. It's backwards compared to most of you. So, how can you give effort when you don't understand? That's what this page is all about. I want you to just, I'm going to be silent for a minute here. I'd like you to read this page to yourself before I go over it. I'm going to be quiet for a minute. I want you to just glance, skim that through yourself. Go. You have this page right on the inside flap of your reference booklet. I want you to get in the habit of using it because, as you see from the title, it's like, what can you do when you don't know what to do? So these are things you can still do even when you don't understand a problem. 10 things. Let me go over these very quickly with you. 1, did you finger track and read out loud? Did you underline and highlight key words? That's called filtering. Numbers and units. Did you at least try to draw a diagram, list given information, and cross out information as you put it on the diagram and the list? You'll see this icon. It says no naked diagrams. Don't ignore the diagrams. Did you trace and sweep angles, trace and stretch lines? Did you trace every aspect of the diagram? Did you recite, say out loud what you learned from today's lesson and previous video? Did you skim through your reference booklet and the DPTP, that's the yellow section in your reference booklet, definitions, properties, theorems, and postulates for related information? Did you actually write out all equations with two sides and an equal sign? When you worked with equations, did you circle, plug, check? Number 8, if you solved for a variable, did you try to plug it in somewhere else? 9, very important. Did you actually close your eyes and try to visualize the information you've been given? Just take a moment, say the information with your lips, and try to visualize it in your head. Close your eyes and do that. That it activates your visual cortex. And the most important, did you really put an effort into understanding the problem, or are you just being passive? I want you to get this through your head. Effort is what gives you understanding. It's not the other way around. You don't understand first and then give effort. Okay, let's actually put some of these techniques to practice. Ready? You're on this page. I'm just going to read this out loud. Mr. Fareed wants to create a rectangular cement patio in his backyard along the side of his house. The length of the backyard is 8 feet longer than the width. Each bag of cement costs $6.50 and will cover 12.5 feet squared. The perimeter of the backyard is 64 feet. Tax on the subtotal is 10%. Find the total cost of the cement backyard. Just look at that for a second. Now, I don't actually want you solving it this moment, but I want you to give me your first gut reaction. As I read this, emotionally, how hard does this problem feel to you? Does it feel like it's going to be a very, very easy problem? Or is it going to feel like, oh, I'm just scale of 1 to 5, I'm dying here? I'd like you to circle your first emotional gut reaction. How hard do you think this is going to be? Okay, before we actually solve that particular problem, we need to recap a few things. I need to review with you the concept of perimeter in a rectangle and area. Perimeter, I want you to think picket fence. Perimeter, picket. Perimeter, picket. Say it twice with me. Perimeter, picket. Perimeter, picket. So when you do perimeter, put your pencil there. I want you to always physically trace it like you're tracing the picket fence around a yard. Notice I put a little arrow that tells your brain you're going around. Label your length and your width. So think of it as a picket fence. So technically, for perimeter, all we do is we just add stuff up. You walk it around and you add it up. We have a width plus a length plus another width plus another length. You are welcome to just write the equation exactly like this. Width plus length plus width plus length. Or the more common way of looking at it is the fact that we have two lengths for a rectangle plus two widths. But just remember perimeter picket fence. Area. Area is like the grass of a yard. So I'd like you to shade the grass and always shade area. And of course, that's simply going to be the length times the width. Let's put this to usage. Okay, I'm going to model what I expect to see you start using in class, which are these first 5 steps. Watch. Filter. Draw a label list, cross out. Filter. Draw a label list, cross out. Say that with me. Filter. Draw a label list, cross out. So we start with problems. Number 1, we read every problem first. Put your finger here, please. Now, as I read aloud, I want you to read aloud with your finger or your pencil on paper. And you don't have to draw these. I'm just showing you how your finger should track. Ready? Read out loud. Mr. Fareed wants to create a rectangular cement patio in his backyard along the side of his house. The length of the backyard is 8 feet longer than the width. Each bag of cement costs $6.50 and will cover 12.5 square feet. Perimeter of the backyard is 64 feet. Tax on this total is 10%. Find the total cost of the backyard. So you should have read that out loud with your finger tracking in all those lines. Now, filtering means you go back and we're going to highlight or underline keywords and all numbers. So get out a highlighter or you can use a pen. Mr. Fareed wants to create a rectangular cement patio in his backyard along the side of his house. The length of the backyard is always an equal sign, 8 feet longer than the width. Each bag of cement costs $6.50 and covers 12.5 feet squared. The perimeter of the backyard is 64 feet. Notice, is an equal sign. Tax is 10%. Find the total cost. When it comes to the actual question, I always like to box it and put a giant question mark to make sure I actually answer the question. Now, what we just did was filtering. We do all 4 of these. We're going to draw a diagram, label the diagram, list and cross stuff out as we go. So everything in this paragraph is either going to go on a diagram, and if it doesn't go on a diagram, it's going to go on a list. Ready? Okay. It says, Mr. Fareed wants to create a rectangular backyard, so we're going to draw ourselves a rectangle. Ta-da! Cross it out. I took care of that rectangle. The length of the backyard is 8 feet longer than the width. The length, watch carefully, is, that's an equal sign, 8 feet longer than, that's a plus concept, than the width. Okay, so here's our width. And the length is 8 feet longer than, more than the width. Now, I didn't say 8 times the width, 8 times longer. It said 8 feet longer than. So that's a plus concept. So now I have it labeled. My width, and there's my length. Took care of that. Cross it out. Each bag of cement, so we're going to put cement on the patio. So there's our cement. So showed the cement. Each bag of cement, that's not on my diagram, that's on my list. Each bag costs $6.50 and it covers 12.5 feet squared. So each bag is going to cover 12.5 square feet. I'm done with that. The perimeter of the backyard is 64 feet. So that's going to go in my list. Perimeter equals 64 feet. That means when I walk it around, notice the little arrows, so that tells my brain I'm going around. My walk around perimeter is 64 feet. Tax, that's going to go over here. Tax, 10%. Took care of this. And my ultimate question is find the total cost. So I always like to box that and highlight it. My ultimate question is, how much is this backyard going to cost? Okay. So when you're done with these first 5 steps, I'll label this cross out. If you're following my instructions, in all honesty, the original problem should be absolutely mutilated. If you have a nice, pretty, clean, absolutely untouched paragraph, you are not following my brain and hand problem-solving techniques. Okay? If you were, it would be just about mutilated. Okay, our goal is to figure out cost. Now, a lot of you, your brain's overwhelmed right now. You're like, I don't know where to start. So, instead of asking yourself, what should you do? How should you start this problem? Just ask yourself, well, what kind of information do you have? Let's look at what we actually have. We have the perimeter, so why don't we at least write that out? I know my perimeter is 64 feet. Well, what else do we know? You can write this out, can't you? You can at least write out how we find perimeter. Perimeter is going to be 2 lengths plus 2 widths, right? Do I know for sure if I need that equation? I don't know. Can I at least write it out? Sure. Again, what can you do? Let's see, what else could we do? Can you circle, please, the fact that the perimeters are the same? Circle that. Can you circle the 64, please? So if the perimeters are the same, we can take that 64 and we can plug it in right there. Now we're starting to get some numbers going on here. Equals. The problem over here is I have 2 separate variables. That's not going to fly. So, let's look and see what we actually have. Can you circle that length? Now come up here. Do you see length anywhere else? Aha. See, they're the same. Circle them. Connect with an arrow. Connect it. Physically draw that arrow, please. Which means we can substitute. Physically pick it up. This means circle, plug, check, circle it. We can substitute at W plus 8 wherever you see an L. So we're going to substitute it. Why? Because we can. Guess what? We're down to 1 variable now. Why don't we go ahead and actually solve for that variable? So we're going to distribute. Just keep solving here. You can kind of do your own math here. All right. So we solved for a variable W. Now, don't get all happy just because you solve for a variable. You always ask yourself, can we do anything with the variable? And the answer is, of course, yes. So we're going to circle that 12, and we're going to put it wherever we see W. We're going to put a 12 here and a 12 there, which means let's get nothing but numbers now in our rectangle. 8 plus 12, that's 20. And then that's 12, that's 20, that's 12. Now we have all our sides. Our ultimate goal is to figure out cost. And to get cost, we have to know how many bags of cement. Now, physically say that cement is not a perimeter issue, it's an area issue. So let's write out our equation for area. We have our length. So let's circle, plug, chug. Circle length, circle it. Get your pencil on the paper, actually circle it. This helps your eyeballs pick up the right stuff. Come up here, circle the length, and plug it in. Ready? Circle the W, physically come up, circle the 12, physically come back and write out the 12. And now we're going to go 12 times 20, which basically you just do 12 times 2, which is 24, and we add a 0. And then that's going to be your area feet squared. And you keep asking yourself, so the area of our patio is 240 feet squared. But each bag of cement, we know, covers 12.5 square feet. So we're going to divide by 12.5 feet squared to figure out how many bags we're going to actually buy. Okay. So if you do this a couple times, you can see that we're going to do 240 feet divided by 12.5, and we need 19.2 bags. But you do not walk out of Lowe's or Orchard Supply or Home Depot with 19.2 bags of anything. So we're actually going to be buying 20 bags. So we're going to buy 20 bags, and they're $6.50 each. So we're going to get our money here. 6 times 20 is going to be 120. And then half of that. So we have here 20 bags times $6.50. We're going to be spending $130. But wait, there's more, because there's this lovely thing called tax. Tax is 10%, so 10% of 130 is simply, you move the decimal over once, it's $13. So final cost, bring down the 3. $143.00. So what we did is we did equations, 2 sides with an equal sign. We circle, plug, chug. We box and label our answers as we found them. There's the width. There's our length and our width and our area. So that is one example of what's called brain and hand problem solving. Now, I want you to take a shot, just one problem, one measly problem. I want you to do this problem by yourself. Pause. Welcome back. Let's see how you did here. So the first thing you should have done was filtered. So it says, Miss Johnson wants to plant a flower marigold border around her small herb garden. The herb garden is rectangular, and the length of the garden is 3 times longer than the width. The area of the garden is 108 feet. Wherever we see is, we're going to put an equal sign. It takes 2 pots of flowers per linear foot to create the desired border. The cost is $3 per pot. How much will it cost to plant a border? So now we do, that's our filtering. Draw, label, list, cross out. We have ourselves a rectangular herb garden. The length is 3 times longer than the width. So that's 3 times the width. So there's our width, and our length is 3 times the width. Okay, took care of that. It's rectangular, 3 times, yada, yada. What else do we know? The area, the actual area. So I'm going to just shade that so I recognize its area. The actual area of the garden is 108 feet squared. Took care of that. It takes two pots of flowers per linear foot. So for every foot, because we're talking about the border here, for every foot I'm going to be buying 2 flower pots. Of marigolds, which are usually yellow or orange. Okay, so for every 1 foot, we're going to do 2 pots of flowers. Take care of that. Each pot of flower costs $3 each. Take care of that. How much will it cost? So ultimate goal is cost again. So cost, question mark, box. Okay, once again, if you did this Miss Way's version, brain in hand, your original problem should be absolutely mutilated. And everything belongs on either the diagram or the list. Draw, label, list, cross out. Now, we start working the problem. We know the area, which is, if you shade it, the area is 108 feet. You're like, I don't even know where to start. Well, hopefully, you at least wrote the area equation out. So we know area equals length times the width. And then you start circle plug checking. Well, I know my area is 108 feet, so I'm going to draw an arrow and I'm going to plug it in. Get in the habit of drawing arrows to connect stuff. It helps your brain not get lost. So I have 108 equals. And I circle my length. I want to get down to 1 variable, so I'm going to circle, pick it up. I'm going to plug it in right there. 3 times W. And then I bring down my other W. Okay, now I'm down to 1 variable. I'm ready to solve. You might have gotten stuck here. W times W is not 2W. W times W is W squared. W plus W is 2W. So a few of you got stuck in this problem because you didn't get past that simple concept. W times W is W squared, not 2W. So from here we solve. So we have 108 equals 3W squared. We want to get W squared by itself, so we divide by 3. 3 goes into 10 3 times, 1 left over, so it's 36 equals W squared. The opposite of squaring is square rooting. So W equals the square root of 36, which is 6. So we know that our width is now 6. And our length is 3 times W. That means our length is 18. Now we want border. Border is a perimeter concept. So draw a perimeter. And we have 6, 18, 618. So we know that for our border, we just add this up, 6 plus 18, 24, 24. So our perimeter is going to be 48 feet. Now for every foot, I need 2 flower pots, right? For every foot, we want 2 flower pots. So that's going to be 48 times 2. So I know I need 96 flower pots at $3 each. It's basically 96 times 3. I told you not to worry about tax this time. And you're going to be spending about $288 just to get the border there. Okay, I'd like you to rate on a scale of 1 to 5. How hard did this feel? Remember, a scale was the 1 being the easiest thing you ever did. Number 5 being I'm dying here. On a scale of 1 to 5, to you, just emotionally, how hard did this feel? I'd like you to write that on your notes. It's going to give me some interesting feedback here.